You know that feeling, right? You pick a line at the grocery store and somehow the other one always seems to move faster. Well, it turns out there's a science to that. Today, we are diving deep into the hidden world that governs every single line we've ever stood in, from your morning coffee to the incredibly complex dance of a modern smart factory. And believe me, that's not just some catchy phrase. Understanding how and why people or things wait in line isn't just about customer satisfaction. It's actually the key to unlocking efficiency for entire systems, predicting where the next bottleneck will be, and making everything from manufacturing to healthcare just run smarter.
So to get this, we've got to rewind a bit. Our story starts in a world where waiting in line was seen as a simple, orderly thing, something you could actually predict with pure mathematics.
At its heart, what we're talking about is called queuing theory. And really, it's just the math of waiting. It's all about building models to understand the flow. How do people show up? How long do they have to wait around? And how do they finally get served? The whole point is to answer questions like, hey, how many cashiers do I actually need to keep the wait time under 5 minutes? Early on, mathematicians came up with these really elegant models to try and bring some order to the chaos. Like the classic M/M/1 model. It assumes that both when people arrive and how long it takes to help them are completely random. That's what that fancy word Markovian means. It's just a constant average rate, totally independent of whatever happened before. A simple call center is a perfect example. These models are super powerful, but they all depend on one huge assumption, that the world actually behaves according to their neat and tidy rules. And right there, that's where we hit a wall. Because the real world, it's almost never that neat and tidy. It's messy, it's chaotic, and it's way more complicated than these clean old-school models can possibly handle. And this really is the heart of the problem, you see. These foundational models are basically built for a world that, well, it doesn't really exist. They assume a kind of stability and predictability that reality just doesn't deliver. I mean, just picture a modern smart factory for a second. A machine suddenly breaks down. Boom, that's a system interruption. Different production lines are all connected, so a delay in one causes a jam in another. Those are networked interactions. And the people working there, they don't always act like perfect, predictable robots. These are the kinds of real-world problems that just completely shatter those old assumptions. Which brings us to the million-dollar question that's driving all of the new thinking in this field. If the old maps don't match the world we live in, how do you find your way? How on earth do you model a system that feels like pure chaos? Well, the answer, it turns out, is to completely flip the script. You stop trying to force the real world to fit into your neat little model. Instead, you build a model that learns from the real world. You let the data do the talking. This slide really gets to the core of this massive shift. On the left, you have the old way. You assume you know the rules. But the new approach, the Structural Causal Queueing Model, or SCQM for short, it doesn't assume anything. It acts more like a data detective. It sifts through all the system's data to discover what the real rules are. And this is a total game changer, because for the first time, we can model the messy reality of a system without having to oversimplify it first. So how does this actually work? It's pretty cool. First, it uses machine learning to dig through the data and find the real cause and effect relationships. Then, it uses those rules to build what's called a digital twin, basically a perfect virtual copy of the real-world queue. And here's the magic part. You can then experiment on this simulator. What if we had another server? What if this machine runs 5% faster? You can see what happens without any of the real-world risk. Okay, so we've got these incredible data-driven models that can handle the chaos of complex systems. Problem solved, right? Well, not quite. Because there's one variable that is more unpredictable than any machine. Us. People. Think about it. Unlike boxes on a conveyor belt, people in a line are strategic. We look around, we observe, we think, we make guesses, and modern queuing theory absolutely has to take our human psychology, our decision-making, into account. And this is where things get really interesting, because now we're dipping into the world of game theory. A pure strategy is a simple, fixed rule. I always join the shortest line, period. But a mixed strategy, that's more like a gamble. It's when you look at two lines and think, that one's shorter, but this one has someone with way fewer items. You know what? I'll take a chance on this one. That's a mixed strategy, and it makes predicting what people will do so much harder. This all leads to this fascinating idea from game theory called the price of anarchy. So, picture the system's performance when everyone just does what's best for them. That's the lower bar on the chart. Now, imagine if everyone was perfectly coordinated to get the best possible outcome for the whole group. That's the higher bar. That gap between them, that's the price of anarchy. It's the efficiency we lose simply because we're all acting on our own instead of together. So, we've got these complex systems on one hand and unpredictable people on the other. What's the takeaway here? What do we do with all this? Well, we use it to design smarter queues and ultimately better systems for everyone. So, if you're managing a system, what does this actually mean for you? Well, you've got a whole new playbook. It means you can use information as a tool. Think about those signs at the airport that show security wait times. They help guide our choices. It means the design of the physical space matters. A pleasant place to wait is less frustrating. You can use data to figure out if your customers are the predictable type or if they're gamblers. And most importantly, you can use those incredible digital twin simulators to test any idea you have before it ever affects a single real person. When you put it all together, you arrive at this really powerful idea. In our hyper-optimized world, the next huge leap forward in efficiency probably isn't going to come from a slightly faster computer chip. It's going to come from fundamentally rethinking the very experience of waiting. It's going to come from designing a smarter line. And that leaves us with one final thought to chew on. How is your world, your business, your workplace designing its queues?